All right, we are recording now. So I was going to do a recap of dimensional analysis. It would be more helpful if you have your homework packet from yesterday. And I want to make sure we really get an idea of how to use dimensional analysis and how to set the problems up. So you need in front of you, you need a calculator with you so you can check your answers. But we're going to look at this dimensional analysis. Works everywhere, even on ORF. I'm going to do just a little bit of notes with this, so if you have your home or your notes, then that would be helpful too, Ms. Anya. Of course, come grab one. Anyone else need a homework packet? There's one. There's one. Okay. So dimensional analysis has one main purpose. What is that main purpose? Why do we use it? We're trying to get from one unit to another, right? So dimensional analysis is a means for converting units. Okay. And the focus is using this fence method where we're putting some starting unit and then we're using conversion factors along the way. You can use one conversion factor, you might use two, you might use 17. Now you can hope that I never give you one where you need 17 conversion factors. Sound off? Okay. But most of them, I'm pretty much going to limit it to like 2 or 3 conversion factors. 3 will be common next week. Okay. So when we're converting units, we need these conversion factors. Well, conversion factors are essentially you have two things that are equal. They're the same value. A very common one that you've heard of, how many feet are in 1 yard? 3 feet, right? So when I'm writing out my conversion factor, I can write it as a fraction. Well, how do I write it as a fraction? 1 yard over what? 3 feet. Anything divided by itself is 1. So the idea is that a conversion factor is effectively a factor of 1. You're not changing the amount of the unit at all. You're not changing the amount of the measurement. The measurement's the same. It's just you're changing the units. Okay? So this is one way. Or you can write it as 3 feet over 1 yard. Okay? So if I'm going to go ahead and convert between, if I've got, say, 47 feet, let's make it easier, 48 feet. If I'm going to plug in my conversion factor, I want feet to cancel out. So how do I write my conversion factor in? I want the feet on bottom. 3 feet on bottom, 1 yard on top. So that's my conversion factor to get feet into yards. Well, 48 divided by 3 is how much? That's 16. So this is 16 yards. Okay? So that is the very simple explanation of what dimensional analysis is. You've worked with feet and yards before in your life, so that's not so bad. The reason I had you do Planet ORF was because now we have these units that make no sense. We don't know what they are. But we don't have to know what they are. We just need to know what the equivalence conversion factors are. Okay? So are there any of them on your homework that you want to look at specifically? Or I'll just pick one. Yeah. Number 8. Okay. So number 8, it says, if you flip in your homework packet, find number 8, it is, if Q Dropa buys Momo at the price of 33 binks per stig, what is the cost in chanks per job? So we have 33 binks over 1 stig. Okay, so maybe this is equivalent to, this is the same idea as the dollars per pound or dollars per ounce. Okay. So we have 33 binks per stig, and we want to convert this into chanks per jop. So yeah, and you picked a good one because this one doesn't have just one unit being converted. It actually has 2 units being converted. So instead of maybe dollars per pound, you're looking at cents per ounce. Or in a different kind of units, instead of miles per hour, you're converting to meters per second. You have to convert each unit separately. The miles into meters, the hours into seconds. So in the same way, binks are going to be converted into chanks. Stigs will be converted into jops. Okay? So if I'm going to do this, I'm going to start with my 33 binks over 1 stig. And Yen, you pick. Which one do you want to start with? The binks or the stigs? All right, so what is the conversion? How am I going to get binks into chanks? Yeah, so in this currency we have 1 bink, 15 chanks. I need the binks to cancel, so how do I write my conversion in? 15 chanks on top, 1 bink on the bottom. Bink is on top and bottom, so divide bink by bink is 1. It goes away. Well, now I have the unit of chanks on the top. I'm good with that. But as it's written, if I just stopped here, I would have chanks per stig. I want stigs converted into jops. So if I'm looking at my conversions, what is my conversion from stig into jops? It's 11 to 1, right? So 11 jops is 1 stig. So when I write this in, where does the stig go? On the top. 1 stig over 11 jops. Chanks stays, stigs go away. So now I have chanks and jops. That's what I wanted up here. Okay, so that's the unit that I wanted, so I'm good. I don't need any more conversion factors. So I just take 33 times 15 divided by 11. This is where your calculator is handy. You also might notice 33 divided by 11 is how much? So 3 times 15 is 45. So we get 45, and now I need units on my answer. If I don't put units on my answer, I have done nothing. Okay, what are the units? Chanks per job. Okay? Does this make sense? Okay. This is the idea. I am mostly focusing on, can you do this process of doing the factor label method, using the fence, writing in all of the units as required. If you don't put units in, I will not grade it because I have nothing to follow. Okay? I'm looking at, can you correctly match up where conversion factors belong? Okay. Sam Hole. That will work, but I want you to be able to do this because I want it all in one factor label method. I'm trying to see, can you see how these units should be canceling out? Because you're eventually, there's always there's multiple ways to solve a problem. I agree with that. This one's the easiest one to grade. Isn't that kind of rotten? So I do make concessions, like when it gets to this kind of thing where you're doing 2 units, I understand when students want to separately convert them. I'm okay with that, but I really want you to practice so that you can do it all in one. Okay? Cool. Any of the other ones give you trouble? Or any of the other ones you wanted to see? Roman. The very last one. All right. The last one says Momo is shipped from the extraction site to the processing plant at a speed of 71,280 hofas per minulo. Express this speed in torps per blorp. Okay, this one's another one where you're converting 2 units one after the other. So I'm going to erase this, get some more space. We have 71 1,280 hoffas over 1 mimullo. And I'm trying to convert this into torps per blorp. Okay. So I'm going to rewrite 71,280 hoffas, 1 mimullo. Roman, which conversion factor would you like to start working with? The hoffas. So hoffas are going into torps. Is there a hoffas to torps conversion? Yeah, there's one that goes directly from hoffas to torp. So how are you going to write that in? One torp over 6 hoffas. Hoffas are now gone. I have torps. I am done with that conversion or that particular unit. Now I can work on mimullos to blorps. Is there a conversion from mimullos to blorps? Convoluted, yeah. This one doesn't go directly. The only unit that has mimullos in it goes mimullos to nilos. So as we're going from mimullos to nilos, is there one that goes from nilos to blorps? No. Again, have to go from nilos to wers, and then wers to blorps. So you're going to use all 3 of these conversion factors as you solve the mimullos to the blorps. Okay? So this first one, what will be the first conversion that we put in? So mimullos to nilos. How many mimullos? How many nilos? So 5 mimullos on top so that the mimullo cancels, and we will have 22 nilos on the bottom. Mimullos goes away. The next conversion is my nilos to wers. Where does the nilos go? On the top. So 1 nilo to 3 wers. Uh-oh, I'm out of room. I don't want my answer in nilos. I don't want my answer in wers. My last conversion, I have to convert wers into blorps. So I put wers where? On the top. How many? 4 wers over 9 blorps. All right. This is kind of a mess. So now we have, please work. Hooray! 71,280 times 1 times 5 times 1 times 4, and I'm dividing it by 6, the quantity of 6 times 22 times 3 times 9. So one thing I want to make sure and point out is this down here, when you're putting things into your calculator, lots of people make mistakes with orders of operations on the calculator because of the calculator, if you just put 71 times 5 times 4 divided by 6 times 22 times 3 times 9, it doesn't recognize that these are being divided unless you put it in brackets or unless you divide specifically by 6, divide by 22, divide by 3, divided by 9. You know what I mean? Hopefully. So plug this in. How many, what is it? Torps per blorp should you get? How many? 400. 400 even? Yes. Or I didn't get the right answer then. No, just kidding. Hold on. No, I got it. Phew. 400 torps per blorp. Okay? You okay with this? Cool. Any others that you needed to see? So dimensional analysis is going to be really helpful as we move into chemistry things. You're going to be using it pretty much for the rest of the semester. Okay? So using this fence method is going to be very important. All right, so the next part of this then, we are going to apply this to chemistry. What you're going to want to have in front of you is a periodic table which you have in your homework packet. And also, you're going to eventually be using this thing, the mole map. Okay? So the mole map and the periodic table, you might want 2 homework packets out so you have 2 different documents to look at. Or a periodic table in a different spot. Okay? You also are going to need a calculator because we're going to be calculating a lot of these things. All right. Hopefully this all works. We're going to introduce the concept of the mole. How many of you have heard of the mole before? Okay. What? The what? Oh, a little bit different. So that's molar. It still has to do with the mole. Good observation though. Yeah, 6 molar HCl. That has to do with concentration. That's going to be 6 moles of HCl in the liter of solution. So we'll get into that maybe in 2 weeks, I think. Okay. So the mole, it's a little fuzzy creature wearing a cute lab coat, right? Not quite, but we're going to use it when we're determining how much of a particular substance we have. So you have measured chemical quantities, right? How have you measured any of your materials so far? Volume? Mass? You've measured some densities you've calculated densities using measured volumes and masses, right? Have any of you really counted atoms? No, not really. We haven't really counted a whole lot, right? But you can count, maybe. We don't usually count it, but we weigh things out. That is the main way that we figure out how much stuff we have, and we find volumes of stuff. But if we're measuring masses and volumes, does that necessarily mean that if I got 5 grams of one substance and 5 grams of another substance, that I really have the same amount of stuff altogether? Like the same number of atoms? No. Zinc is a lot heavier than hydrogen. So if I have 5 grams of zinc and 5 grams of hydrogen, I have a lot more atoms of hydrogen than I do of zinc because each atom weighs a lot more. Well, the mole is going to help us figure out this counting part. It's going to help us compare substance A to substance B. Okay? Matter is way too small to count. So we're going to look at the mole. How do we figure out the mole? Well, we stick a mole on one side of the balance, and we stick a whole bunch of stuff on the other. And when they balance out, then that's a mole, right? Silly. No. A mole is a counting number. It's going to be kind of like a counting number, like a dozen. How many is a dozen? 12, right? Or there's the baker's dozen. If you want to read about some really creepy history, go read about the baker's dozen. The mole is going to be related to this guy, Avogadro. I'm going to show you a quick video in a few minutes to show you, or to give you a little bit of history about poor little Avogadro, who was misunderstood but appreciated later on. Avogadro's number is the mole. It is equivalent to the mole. Okay? And the mole of stuff, this is the number. 1 mole of stuff is equivalent to 6.02 times 10 to the 23rd items. And what I mean by items, you're probably going to want to write this into your notes, that items is equivalent to particles, molecules, atoms, units, and ions. Put those in your notes right this second. So all of those are equivalent units technically. Like you can use Avogadro's number with particles, molecules, atoms, units, and ions. And what it means is that anytime it says items, that means it's going to be either particles, molecules, atoms, or units. You need to put that value in, or put that unit in correctly. Okay? Short story, it's a big number. It's a very big number. Question is, can you really wrap your mind around such a big number? Maybe. How large is it? Now this slide is just silly, so you don't have to write this stuff down. But a mole of hockey pucks is equivalent to the mass of the moon. So if you have 6.02 times 10 to the 23rd hockey pucks, that would be really heavy. Okay? A mole of basketballs would fill a bag the size of the Earth. That's a lot of basketballs. Best one, a mole of pennies would cover the Earth a quarter of a mile deep. So the mole is a really, really, really big number. Okay? And if you have a mole of some substance, you have that many atoms. That's a lot. Okay, so I have this quick video that we'll watch. Hopefully we don't break any copyright rules by recording the recording. Those of you watching in a different way, you should find the video in the notes and play it from there.
Okay, today we're going to talk about the small birds which are big holes in the ground which grow garden. And some of you might be thinking that the growth under his face is parasitic matter. Well, in this case, the mole is a concept that we use in chemistry to count molecules, atoms, just about anything extremely small. Have you ever wondered how many atoms there are in the universe or in your body, or even in a grain of sand? Scientists are wanting to answer that question. But how do you count something as small as an atom? Well, in 1811, someone had an idea that if you had equal volumes of gases, same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to find out. Fortunately, for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in a small sample is tremendous. For example, you have a balloon with any gas at 0 degrees Celsius and at a pressure of 1 atmosphere. Then you have precisely 602 sextillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in the container. Well, in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gas will take up a lot of space due to the high kinetic energy of gas particles, and it leads to thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sextillion molecules of water. Since Lorenzo Romano, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. He is simply known as Avogadro's number. Now, back to the mole. But not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sextillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or 602 sextillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sextillion look like? Maybe this will help. Streams of water particles with donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketball, you could create a new planet the size of the Earth. You see, the mole of pennies when the day you were born spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we fully have an idea how large the mole is. But how do we use it? You might be surprised to know that chemists use the same way you use pounds by grade spelling for eggs. When you go to the grocery store, you don't go to the dollar counter and ask for 42 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen. When you hear the word dozen, you probably think of the number 12. We also know that a pair is 2, a big dozen is 13, a gross is 1.4, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, the mole conjures up the number 6.02 times 10 to the 23rd. Not a fuzzy we're going to use. The only difference is the other quantities are more familiar to us. So there you have it. The story of the mole. How we got those basketball and how to buy some on the
Well, thanks, Ed. Okay, back to this. So can you imagine the mole? It's tough. Well, let's put it into more practical terms. I'm not going to go around and count up atoms still, right? I can't see the atoms, I can't count out the molecules. So what I'm going to do is use something else, something that's a little bit more practical. How about, I still want to be able to weigh out my substances, but now I need to figure out, well, how many moles is that? Fortunately, there is a defined quantity, the molar mass, which is the mass of 1 mole, right? So the mass of 1 mole of an element or compound is a unique number for each compound, each element. Every element has its own mass. Very convenient. But now I need to know, where do I get that information? You have a really handy resource in chemistry, right? You have it on the walls. You have it in your every single homework packet. Your periodic table. Have your periodic tables in front of you. Notice some information that's on it. What do you know is on the periodic table? There's a whole bunch of numbers, right? What numbers are on the periodic table? The atomic number, and then there's that other number. What is the other number? That's the atomic mass. But guess what? The atomic mass that's on the periodic table is not just the atomic mass, where it's got units of AMU. Lena's trying to tell us it's also the molar mass, right? So that mass that's on the periodic table is not just the mass of atom in AMU, but it's also the molar mass. That means 1 mole of atoms of that element weighs that many grams. I had the hardest time wrapping my mind around that one concept. I still do. You can go through the conversions and calculate out, does it really work out? Or you can just trust me that yes, the mass of 1 atom of, say, hydrogen is 1.0079 AMU, atomic mass units. At the same time, 1 mole of hydrogen atoms, 6.02 times 10 to the 23rd atoms of hydrogen, weighs 1.0079 grams. You can trust me on that. Okay. Now this last little note, anytime you're writing out molar masses, you must use a minimum of 2 decimal places. So put that into your notes. It's a minimum of 2 decimal places. Because if you cut out any more, then you've done too much rounding and then things get nasty. Now, there are some exceptions, of course. Why wouldn't there be? This time it's not hydrogen. It's other elements that are much heavier, like lead and platinum. And on your periodic table, there's actually only room for those heavier ones to only have 1 decimal place. And that's fine. Whatever your periodic table has, you may not cut off any from the quality core one at least. Okay, so round to a minimum of 2 decimal places. All right, then this should be pretty easy. If we're figuring out the molar mass of elements, all we have to do is look at what is the molar mass on the periodic table. So find carbon and put your finger on it. Collectively, what's the mass of carbon? 12.01 in what units? Grams per mole. 12.01 grams per mole. Find aluminum. Plop your finger right onto it. What's its molar mass? 26.98 grams per mole. Find zinc. Plop your finger on it. What's its molar mass? 65.38 grams per mole. So finding the molar mass of your elements should be super easy. Okay. Now the fun part is actually having a visual. You just did zinc, right? So zinc, 65.39 grams of zinc. In this vial, I have 1 mole of zinc. You can pass this around. Find iron. How much should a mole of iron be? 55.85. Well, this is 55.85 grams of iron. That's better. What about lead? .2 grams of lead. Funny enough, it fits in this little vial. 207.2 grams. Come on, right here. But all of these vials, each vial contains how many atoms? 6.02 times 10 to the 23rd particles. All three vials contain the same number of particles, even though they weigh significantly different. Okay? So that's the molar mass of elements. All right, we can also do this for compounds, though. The only difference now is we have to account for all of the atoms within the compound. So if I'm going to find the molar mass of a compound, I first need to know what? Before I even know the molar mass of each element, what do I need to know? How many of each element there is. Well, what do we use to show how many of each element? More collectively, I'm going to write the blank of the compound. The formula of the compound. So the formula is important. Remember all that practice with writing formulas and naming compounds? If you didn't catch all of that last time, it's going to bite you in the booty now. So you want to make sure that you're also practicing your naming. Please, you're making me nervous. Don't put that pen in the light socket. Stop it. Okay. So if I'm looking at water, what's the formula of water always? H2O. That means I have 2 hydrogens and 1 oxygen. So if I'm going to write out the formula, or if I'm going to do the molar mass of my water, I need to account for 2 hydrogens and 1 oxygen. So what does that look like? Well, I look up the masses of each element. How much does a hydrogen weigh? So 1.008 grams per mole. I'm going to put that in parentheses, and I'm going to add to it just 16.00. Put the 00. If you don't, I get mean. So you're adding up 2 times 1.08 plus 16. And what do you get? Do we all agree with that? Are you all calculating it? Are you trying it? Are you engaged? You must practice, practice, practice. Or at least pretend. Don't pretend. Just do it. Do we have agreement? What'd you get, Matt? That's why you got to at least do it. Calculate it out. Do you agree with this value that Lena has shared? You never know. She could tell you the wrong answer on purpose. Wouldn't put it past her. What did you multiply or add together? So we have one confirmation. Sam, you confirmed as well. 18.0158. You round it to 2 decimal places. 18.02 grams per mole. Every time you're writing out a molar mass, you need to put grams per mole as your units. Well, what does this even look like? In the video, it said that it was about 3.5 teaspoons. This is 1 mole of water. This little vial. 1 mole of water weighs 18 grams. That's not very much. That means there's still 6.02 times 10 to the 23rd molecules of water in that vial. That means there's actually 6.02 times 10 to the 23rd times 3 atoms in that vial, because every molecule of water has 3 atoms in it. That's a lot of particles. How about for sodium chloride? What's the formula for sodium chloride? NaCl. So now we're going to add up a sodium and a chlorine. How much is a sodium? 22.99. How much is a chlorine? 35.45 grams per mole. So when you add it up, I'm hearing 58.44. Did you try it? 58.44 grams per mole of sodium chloride. This one doesn't fit in one single vial because it's just a little bit too big. Here's my sodium chloride. This is 1 mole of sodium chloride. That means there are 6.02 times 10 to the 23rd units of sodium chloride. Because it is ionic, we're going to call it units. That also means there are 6.02 times 10 to the 23rd times 2 ions in that vial. Because there are 2 ions in every unit of sodium chloride. Sodium and a chlorine. That's a lot of ions. Okay? All right, next one I have a little bit more practice for you. Sodium bicarbonate and sucrose. These ones are a little bit more complicated of formulas, but it's still important for you to be able to identify the formula, at least the first one. The first one's an ionic substance, so you should be able to name this at this point. What's the formula for the sodium ion? I just heard mumblings. Sodium is Na. What charge does it have? +1. And bicarbonate is what ion? I haven't heard it yet. Is it a polyatomic ion? Yes. So if you're not sure of what it is, should you check your polyatomic ion sheet? It's in your other packet. Bicarbonate. Find it. Guess what? You have your polyatomic ion makeup quiz on Friday. It's what? HCO3. Absolutely. It's a -1, so when we crisscross, we get NaHCO3. So that is the formula of sodium bicarbonate. And then sucrose, I wouldn't expect you to know sucrose. That one is a macromolecule. You can learn that in biochemistry, or if you're like me, you didn't like biochemistry very much. And you fried your way through it. Okay? C12H22O11. That is our second practice. I want you to try calculating out molar masses of each of these at this point. You probably want to document in your notes what the work is that you're showing, so that when I come around and I'm guilty, I will see you. Yeah, both of them. All right, this first one, we have a sodium, a hydrogen, a carbon, and 3 oxygens. How much should it weigh? What do we get? I hear 84.01 from a few people. Do we have confirmation from others? Okay. So 84.01. We have 22.99, 1.0079, 1.01, and 3 oxygens. So we have to multiply oxygen by 3. So it should come out to be 84.01. All right, sucrose, C12H22O11. How much should that one be? $342.2 something or 30. Any others? Around 342, correct? So 12 carbons, 22 hydrogens, 11 oxygens, 342.29. So that one's getting a lot heavier. It's a big molecule. There's lots of carbons, hydrogens, and oxygens. Baking soda is the sodium bicarbonate. One box of this weighs 454 grams. So if 1 mole is 84 grams, then what's that? 5-ish moles. I'm not on my math game today, so I'll do anything. Okay. Then sucrose. Sucrose, 342 grams of sucrose is quite a lot of sucrose. This container is a 500-gram container of sucrose. It didn't seem realistic and reasonable for me to take all of the sucrose and put it into all the little vials when I could just show you this and I could keep on using it and not be worried about it. So if it's full, this would be just less than 2 moles of, it's like 1.5 moles, maybe-ish, of sucrose. That's a big molecule. Okay. Tasty one, too. Very nice. That's our mole. What are we going to do with it? We're going to do stuff. We need to use these molar masses. So it's not just calculating molar masses and we're done. We're actually going to use them. Okay? Chemists use molar masses all the darn time. So I have given you a document that's called a mole map. Find that mole map in your homework packet because it's not in front of you. So I want you to just look at it for a minute. Observe it. See what is connected, why is it connected, what. Take it all in for a second. All right, so in the big circles, what are some things that are in the big circles? Moles? What else? What else other than moles? What do we have? There's masses, there's volumes, there's particles. These are the quantities, okay? So in each large circle, you've got some sort of quantity. Look at the lines. What do you see on the lines? I see Avogadro's number over 1 mole or under 1 mole. What else? Mass percent, molar mass, density. These, everything that's on the line is going to be a conversion factor. Whether you recognize it as such right now or not, every single thing on the line is a conversion factor. Hi.
Permiso.
Por supuesto.
Do you have like classes the next 2 periods the rest of the day that are huge so you can't get up any of your teachers?
Oh, you can have, 4th period is full. But I do have desks that have permeated my classroom and have not left. So you can have some tall chairs. How many do you need?
2? Sure. Even like the little bench to use this in the front?
You can take,
Oh, they're on wheels, so
there's,
it's easier.
yeah,
Okay,
take the
thank
wheelie
you.
ones.
Sorry, apologize. And then Julian, a phone today might be a little late because he's one of our blood donors
Okay.
over lunch or
Okay.
whatever. Gracias.
Por supuesto. I'm recording class too, so children are really going to enjoy this. All right. So what I wanted to back to what I was saying. All of the things that are on the lines are conversion factors. Actually, I should probably write this on the board where people will see it. On this, right? Okay. So I want you to look at like density. What is density equivalent to? Mass over volume. Conversion factor, right? Molar mass is what? Mass over mole. Conversion factor, yes? Another one was mass percent. You don't know about mass percent necessarily yet, but it's going to be mass of A over mass total. This is all conversion factors. So it's very convenient that the lines connecting are how you're going to get from that big one circle to another. Okay? Okay, back to this. Something I should also point out to you is that the mole map is not going to be allowed on the final. Any test that I write for you, you can use your mole map. Okay? So hip hip hooray, any test that I write, you can use the mole map. For the final exam, I can't allow you to write it or to use it because it's not my test and it's standardized, so you can't do it. Okay? They had it on the What? You should show me next time you see one, like I want to see it. Okay. Alright, so your mole map, if you're looking at it again, you can see that the big circles, when you can, anything connecting, this is how you get from A to B. This is how you get from particles to moles. You use Avogadro's number. Now, on your mole map, I want you to add this information on the circles that say particles. There's two of them. Notice the mole map is like a mirrored image of itself, right? So on your mole map, there's two places where you're going to add this information. If you don't add this information, you're going to ask me questions later, and then I'm going to be like, why didn't you add this information? So do this now. Find the particles circle. A circle with particles. And write in underneath molecules, atoms, units, and ions. So you're including that in over on both sides. Come on, little scroller. On this particle circle, you're putting molecules, atoms, ions, and units because they are interchangeable with regards to how this conversion factor is used, the Avogadro's number. Avogadro's number will take on whatever unit you're using as long as it is particles, molecules, atoms, units, or ions. Okay? All right, so how do I use the mole map? Well, it's very similar to how you use any old map, which, how many of you use maps and road maps when you're traveling still? Okay, the number is dwindling. Not many people now that iPhones and Google Maps is widely available. I admit, I prefer that. Okay, turn here. But suppose I want to go from mass of A to moles of A. Or suppose I want to go from Columbus to Cincinnati. I need to figure out my starting and ending points, and then all the roads that connect are going to get me there, right? Very logical. Well, if I'm going to go from mass of substance A to moles of substance A, I just need to find those two things in the mole map. So mass of A, you find it. It's right here. Put your finger on it. Find moles of A. Put your finger on it. What's between? Molar mass. That is the conversion factor that's going to get you from mass of A to moles of A. Just molar mass. Okay? Lena. If it's pure or impure, most likely it's going to be a pure substance. If it's telling you the mass of this substance and it gives you the formula, it's implying that it is a pure substance. It will have to specifically tell you the substance was contaminated with blah, blah, blah for it to be impure. Okay? So in this class, you're not really going to use the impure one. All right, so now what? Well, remember the factor label method? Now we're going to apply it to this, we're going to apply it to this application, people. Okay? We're just going to use the conversion factors and line them up using the fence. So here's the first practice on doing these molar conversions. Very simple one. How many moles are in, or how many particles are in 5 moles of water? The thing you have to do, you have to figure out what is it that you're starting with, what unit are you ending with, put your fingers on the mole map, and then see what conversion factors connect your fingers. So if I'm starting with 5 moles of water, because it's the number that's given, what am I solving for? I'm going for particles. So on my mole map, I put my finger on moles and another finger on particles, and what is in between? Just the Avogadro's number. Okay? So I'm going to start by setting up my factor label method and put 5 moles of water in that first box. And then I need to line up Avogadro's number so that things cancel out correctly. I have to remember that Avogadro's number in this particular problem has units of particles. So I'm going to write that in after Avogadro's number. If you leave it blank with no units, nothing cancel. You have to put the units in. Okay? So 5 moles of water. That means on the bottom, what should I put? I'm going to put in 1 mole, and on top I will put Avogadro's number. Now your job is to punch things into your calculator accurately. So have at it. With enthusiasm. Did you get it, Shukri? What do you think? Why do you think you got it wrong? It's a weird number, right? But you have a weird number in the calculation. Avogadro's number, it's a weird number, right? You're not used to working with exponents of times 10 to the 23. So you have to overcome that hurdle. 3.0 times 10 to the 24 particles. Are we in agreement with that? Did other people get this weird, possibly wrong answer? If we all got this possibly wrong answer, we're probably right, right? I think we're right. But now we have to do one thing. We need to check significant figures. How many significant figures should I end with? I need to end with 1. I started with 1. Anytime I'm doing factor label method, I need to end with the same number of significant figures I started with. The reason being, I don't want the simple fact that I have done a conversion to affect how many significant figures I have. If I paid for all 1 of my significant figures, by golly, I better end with 1, right? Or if I had 17 significant figures to start with, I need to end with that. But what I have to do is make sure that my conversion factors, they shouldn't limit me. That means if I had 4 significant figures to start with, I probably need 4 significant figures in my conversion factor. I should get a better, I should get more decimal places. Avogadro's number is known to way more decimal places. I'm just telling you 6.02 because it's easier to remember. Okay? So you should not be losing significant figures just because you've done a conversion. Okay? So I should end with 1. That means I should have 3 times 10 to the 24th particles. Awesome? That's how many particles are in 5 moles of water. That's in 5 of these vials. If I had 5 vials, that would be 3 times 10 to the 24th particles. Yikes! That's a lot of water particles. But not really that much water. Got more in this, right? Okay, let's try another one. We have how many moles of carbon are in 26 grams of carbon? Am I going to need Avogadro's number here? I just need molar mass in this one. So Avogadro's number is not used unless you have particles, ions, atoms, units, molecules. That is the only time Avogadro's number is used. I often have students who will want to use it in every problem. Note, they're pretty rare. Okay? You're not going to use Avogadro's number a whole lot in chemistry as you proceed onward and outward. Okay? But I do have 26 grams of carbon, and I'm solving for what? The moles. So Lena told us we need to use molar mass, or somebody told us that. Okay. What's the molar mass of carbon? If you look at your periodic tables, 12.01 grams of carbon. So I'm going to be using that value. I'm going to put my 26 grams of carbon in to start with. How do I write my grams per mole or moles per grams? What's going to go on bottom? I want grams on bottom. So I'm going to take that number, the 12.01, put it with grams on the bottom. I'm going to leave 1 mole of carbon on top. It's always the easiest to figure out what goes in the bottom right corner because it's whatever you had in the top left corner. Grams carbon, I need grams of carbon down here. So 26 divided by 12.01, how many moles of carbon is this? I'm hearing 2.2. Check it if you haven't calculated it. Never just trust your peers. Sometimes they lie to you. Okay. Are we in agreement? 2.2. And it's 2 significant figures. 2.2 moles of carbon. I must have units on there. If I don't, my answer means nothing. Okay? Okay. I think I'm going to skip this next one. You can do this one on your own if you'd like. Da 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 da. Let's do instead this one. Find the mass of 2.1 times 10 to the 24th molecules. And actually that should say units. There we go. Units of sodium bicarbonate. So 2.1 times 10 to the 24th units of sodium bicarbonate. Put your finger on that circle on the mole map. What circle did you put your finger on? Particles. So even though it says units, it is equivalent to particles. What are you solving for? You're solving for mass. Put your other finger on it. What connections do you have then? I need to go through moles, but I'm going to use Avogadro's number, and I'm going to use the molar mass. So those are the 2 conversion factors I need, which is why I've even given you this hint that you're setting it up with 2 conversion factors. So you're going to start with your 2.1 times 10 to the 24th units of sodium bicarbonate. You're going to write that there. And now I want you to plug the conversion factors in correctly. So take a second, put those in the right places. this first conversion factor? So we've got moles per Avogadro's number. So 1 mole equals 6.02 times 10 to the 23rd. Units this time. Seems kind of weird. The units are units. Thanks, chemist. How am I writing it in? What's going to go on bottom? I need this part, the Avogadro's number, to be on the bottom. And the 1 mole is going to be on top. That way my units cancel out. The units of units cancel. But now I have moles on top. I don't want moles, I want mass. The molar mass is going to go on the bottom this time. Or on the top, just kidding. 1 mole is going to go on the bottom. Did you already calculate the molar mass of sodium bicarbonate? You sure did. How much was it? 84.01 grams per mole. So it goes grams on top, 1 mole on bottom. Moles cancel out. And you calculate this out. You didn't have the work shown yet. Calculate it now. You're using the EE button for your exponents. You don't want to end up with, if you end up with something like times 10 to the 47, you know you've made a mistake with exponents because you're not ever going to have that. That's an odd one. Okay, 10 to the 23rd may seem odd, but 10 to the 47 is worse. Okay. How many grams should we have gotten from this? Here, 290. You okay with that number? So your calculator tells you what? We're in 293 grams, but I want how many sig figs?
2.
Just 2. So 290. 290 grams of sodium bicarbonate. Okay. Not so bad. It takes some practice. It takes some working with the factor label method and getting used to how you set things up. Once you're okay with that, it should be easy peasy. Okay. So your homework, you have a molar mass sheet in your homework packet, and really all you have to do for that first part. I'm going to do this. All you have to do for this first part is look up elements and find their molar masses on the periodic table. Okay. Second part, I'm telling you the formula of the compound. I'm asking you to give me the name of the compound as well so that you're practicing naming compounds and writing formulas. We're still making mistakes from what I saw on the test. I'm still making a few mistakes, little tiny things when writing formulas, when writing names. Okay. Show your work. Notice the little bubble. Show your work. Include units. Make sure you're writing down what it is that you're adding up. Okay, so if it's this second one, cesium chloride, you have 1 cesium and 1 chlorine. You're showing those masses. Part B, I'm giving you the name of the compound and you have to come up with the correct formula. All of these are ionic compounds. Make sure you're paying attention to the charges of each of the ions so that you know how many of each ion you need. Okay? Show the formula, show the molar mass. The second piece of the homework, you have molar mass conversions. There's just a couple of rules up at the top. And then you have, what, 5 problems to do? Not very many. I've given you the problem. I'm asking you to give the formula of the substance in question, give its molar mass, whether you need it or not. So some of them you'll need the molar mass, some you won't. But you're still calculating the molar mass. You're identifying what are you converting between, what unit and what unit. And then you're using your mole map accordingly. Set up the factor label method, circle your answer. You've only got 5. Okay? We have quite a bit of time left in class. This is your time to get started working through these. I'm going to discontinue the recording, and those of you not here will get to hear the song later. Don't worry.